Let's continue the study of many properties of Laplace equation, Green's function, and so on. So now I wanted to prove the following theorem. This is called symmetry. Green's function. It is the following statement. Suppose we have a domain D with a boundary gamma. D in Rn. It is a bounded domain with a smooth boundary. And we have a Green's function, g of xy, Green's function. So it is a function has the following property: Laplacian g of xy with respect to y equals delta function x minus y. So it is delta function at the point x. And g of xy for y in gamma is 0, identically 0. So it is a solution of this equation, Laplacian g of xy with respect to y. X is parameter, is delta function at the point x, and on the boundary it is 0. So it is a particular case of the Dirichlet problem. And the theorem sounds this way: g of xy equals g of yx. No, in case x different from y. First of all, I want to remind you for the proof of this theorem, remind you the Green's identity, which sounds as follows: integral over d u Laplacian v minus v Laplacian u dx equals integral over gamma dy. Let me dy. So u and v are functions of y. Integral over gamma u dv d and y minus v du d and y dsy. So ny is the unit normal vector at the point y, and dsy is the element of the area on the n minus 1 dimensional surface gamma. So it is the Green's identity which I proved before, and let us use it. So let us find g of xy. It is a function where x is fixed and y is variable. Can be write the following: integral over d g of x z delta z minus y dy. Yes, we take the Green's function it is it is a function as all other functions for y different from x, and then we put delta function at the point y. No, and integrate. This time the variable of integration is z. Yeah. Now let us substitute this. So it is equal integral over d g of x y x z. I'm sorry, x z. Now Laplacian g of y z with respect to z. Yes, dz. Laplacian g y z with respect to z, it is written here. Let us write y instead of x, z instead of y, and Laplacian with respect to z, respect to the second variable, is delta of the first minus second. So it is this. Let me draw a picture. Say this is this is delta function. This function g. This is our domain D. Yes, this is the function g x y. So there is a point x. G x z. This is the function g y z. It is the point y. Yes, and we want to prove that g. Now Laplacian of this function is g x z with respect to z is delta function at the point x. Laplacian of the function g of y z with respect to z is delta function at the point 1. So it is here. And now let us use the Green's identity. So it is let us replace this, that integral over d. Laplacian with respect to z, g of x z times g y z dz. It is this term. Yes, so instead of this, I put this in the right hand side, plus integral over gamma g of x z, I must say z in gamma, d g of y z d and z minus d g x z d and z g of y z, all this ts at the point z. Yeah. Now here there can be some I would say doubt because this identity was proved for the functions which are say in C2 inside domain. It should be twice differentiable, so that this makes direct sense. And here we have a singular function, which Green's function is not even bounded. It is singular at the point x or correspondingly y. But these we can a little bit modify them. Then it will make sense, and then go to the limit when the radius of modifier goes to 0. Okay, now let us see. this function is 0 on the boundary. This function also is 0 on the boundary, when z is on the boundary. So this part is 0. This 0. So what remains? Integral over d. Laplacian gxz with respect to z is delta function when z equals x. Yes? Delta x minus z. G of y z dz. Yes, x and y are parameters, so the only variable here is z. So what does it mean? It means that delta function for z equal x times this function g of y z, and the integration is simply g of y x. Yeah, by the meaning of delta function. So if you go to the beginning, we start gxy, and after these transformations, we have equals gyx. So this is proof. Okay. How to regard this? No, you can regard this as just formal transformations, formal calculations. No, is the way how such theorems are proved. If you think a little bit, you see that this proof is quite natural. But what I wanted to say, I wanted to explain immediate physical interpretation of this. I will give a couple of interpretations. So, example. Suppose we have a surface, in three-dimensional space, gamma, which is made of metal. Say it is made of foil or of thin metal mesh, and it is conductive. Yes, so the charges can move along this surface, and there is nothing inside, say air or vacuum. And to be sure, it is grounded. Yes. And now let us, what is the Green's function? It has the following interpretation. We put a point charge at the point x. Yes. Then here we put the charge, say q. It is, say, positive charge. There is some small ball, charged ball, and the total charge is q. Yeah. Then we have here some electric field. We have some electric potential phi of y. And this phi of y is nothing but, it satisfies the equation Laplacian phi is 0 in d minus this point x. Yeah? Phi is phi of y. And phi on the boundary, gamma, is 0 because it is conductive and grounded. So this means that phi of y is in fact g of xy. No, with the coefficient, say q. If the charge was q, in corresponding units. So if you put the charge at the point x and measure the field at the point y, then you measure exactly the Green's function g of xy. And this identity g xy equal g yx means the following. So instead of this, you can put the charge at the point y, yes, and measure the field, the potential at the point x, and the result will be the same. So this is the one physical interpretation. Now, other physical interpretation is I would say, hydrodynamical interpretation. Suppose we have a porous body, a porous layer, which is filling some domain D, and around it is a piece of porous material, yes, say sand, and on the boundary gamma it is free. So this means that from here the liquid can go out or come in, flow in freely, yes. Say it is all put in water, in the basin of water, something like this. And you put at the point X, say drill a hole, well, and start pumping water at the point X, then here, and then the pressure, this means that here we have the free communication between this external water, ambient water, and the sand here. This means that here pressure equals, let's say 0. Pressure is also defined up to some constant. This pressure is 0. And if you measure the pressure at the point Y inside this, so we drill here at the point Y, we drill well and measure the pressure here. So we pump it here and measure the pressure here. Or if you pump the fluid at the point Y and measure the pressure at the point X, you will get the same result. So this is symmetry or symmetry of this Green's function. No, it has many different interpretations. Say, if you have a room, you are staying here and speaking out at the point X, and somebody is at the point Y and receives your sound, which was produced at the point X, and so the energy of the sound, the intensity of the sound at the point Y, if it was produced by a speaker at the point X, is also a Green's function. Yes, we can say, put like in the sound studios, make these walls of thick layer of, say, cotton or something like this, which perfectly absorbs the sound. Then it will more or less ensure the boundary condition that on the boundary the intensity is 0, it is completely absorbed. Yes, and then you start speaker is here, receiver is here, and we have some transmission, say, coefficient between x and y. And it is again a Green's function, yeah? And so if you change places of the source and receiver, put your microphone at the point x and speaker at the point y, then the transmission coefficient, we get the same transmission coefficient. Yes, so I heard exchange at the Department of Differential Equations of university where I studied. So somebody was speaking at this end of the room, the other was staying here. He said, I don't hear you, what you are saying me, please speak louder. And that replied, but I hear you. Yes, so by the symmetry theorem you should hear me as well. Yeah, so it was a real exchange which is difficult to invent. Okay, so this is what we have about the symmetry of Green's function. Next will be other topic, and this property will pop up a little later. So let us make a small break for now. Have a good time and have some coffee. Bye.